Hello everyone and welcome to Mechatronics, Robotics and Aerospace tutorials. In this tutorial we explain the concept of homogeneous transforms and we explain how to derive homogeneous transform matrices. Homogeneous transforms are very important in robotics and aerospace and they have a number of applications. Briefly speaking, homogeneous transform matrix illustrated over here encodes rotation and translation of two coordinate systems. The homogeneous transform matrix enables us to transform coordinates of points from one coordinate system to another coordinate system. Okay, let's start. For the presentation clarity, we consider a two-dimensional geometry shown over here. However, everything explained in this tutorial can easily be generalized to three-dimensional geometry. Let's analyze this figure over here. Essentially, this figure shows two coordinate frames or coordinate systems, F and B, as well as the point P. This frame F is called the fixed frame, or in the mechanics terminology, it is also called the inertial frame. On the other hand, the frame B can translate and rotate. You can see that B frame is translated from the origin point F, and it's over here, and then it's being rotated for the angle theta. The frame B is called the body frame. This is because we usually assume that the frame B is fixed to the rigid body that can translate and rotate with respect to the frame F. Let us explain this notation. The points F and B are the origins of the frames F and B. XF and YF are the coordinate axes of the frame F. Similarly, XB and YB are the coordinate axes of the frame B. This vector here, RPF, is the distance of the point F, that is the origin of the frame F, to the point P. The projections of this vector will be expressed in the frame F. The vector RBF is the distance of the point F, or the origin of the frame F, to the point B, or the origin of the frame B. The projections of this vector are expressed in the frame F. Then we have this vector RPB. This vector is the distance vector of the point B, or the origin of the body frame, to the point P. And the projections of this vector will be expressed in the frame B. The angle theta or theta is the angle of rotation of the frame B with respect to the line parallel to the axis XF of the frame F. And over here, I denoted this line by using dashed line. We can interpret this angle as the angle of rotation between the frame B and the frame F. The vector RBF can be interpreted as the translation vector between the coordinate frames F and B, and this angle theta can be interpreted as the angle of rotation between B and F frames. Let's now formulate the homogeneous transform problem. Here's the homogeneous transform problem formulation. First of all, we assume that the following quantities are given. We assume that the coordinates of the point P in the body frame B are given. That is, we assume that the projections of the vector RPB in the body frame are given. Then we assume that the angle of rotation theta of the body frame B with respect to the fixed frame F is also given. Then we assume that the vector RBF and its projections describing the distance between the points F and B are also given. The projections of RBF are expressed in the fixed frame F. Then, under these assumptions, we want to determine the homogeneous transform matrix denoted like this, T b with respect to a that satisfies this equation. Let us interpret this equation. This vector over here, consisting of rpb vector and a scalar 1, takes into account the coordinates of this point P in the coordinate frame B. Then, we multiply this complete vector by our homogeneous transform matrix, and as the result, we obtain rpf vector and 1 over here. This complete vector on the left hand side actually produces the coordinates of the point P in our fixed coordinate system. That is, this complete homogeneous transform will take into account translation and rotation of B with respect to F, and it will encode these operations to enable us to quickly transform the coordinates of the point P from one coordinate system to another. Before we continue, let's explain this notation. Over here you can see the left subscript and you can see the left superscript. The left subscript is the input frame. That is, it's the frame B in our case, and the left upper or the superscript is actually the output frame. That is, this homogeneous transform takes coordinates from B and produces coordinates in A. And this is how you should interpret this notation over here. Then let's explain the notation that you can see over here. So what is written over here? Whenever you see R, R is a distance vector. Then the subscript is actually the point. For example, over here, this is the distance vector to the point P, this is the distance vector to the point B, and then you will see this left superscript. The left superscript denotes two things. First of all, it denotes the point with respect to which we measure the distance. For example, in this case, we are measuring the distance with respect to this point, and at the same time, this left superscript also denotes the frame. That is, it denotes the frame F. And often, if you see something like this, then the coordinates of the vector RPF are actually expressed in the coordinate frame F. And I will explain this later on in this tutorial. The problem of deriving the homogeneous transform matrix can be split into two parts. In the first part, we need to derive the rotation matrix. So let's do that. Let's analyze this figure over here. Over here, I simply isolated my body frame B, and this horizontal line is actually a line that's parallel to the axis XF of my fixed frame. Then, over here, I define a new frame called S. The axes of this frame S are actually parallel to the axes of the fixed frame F. That is, this frame S is simply translated with respect to my fixed frame F. And I assume that the origin of this frame S is exactly at the point B. Now, by analyzing this figure over here, we can see that the body frame is rotated for the angle of theta with respect to our frame S. Our first goal is to express the projections of the vector RPB in the frame S. That is, we need to compute XSP and YSP. Namely, here's our vector RPB, and the orthogonal projection of this vector onto the axis XS is obviously this distance over here, which is denoted by XSP. Similarly, the orthogonal projection of our vector onto the YS axis is this distance over here, that's denoted by YSP. To simplify the notation, let us introduce R. R will be the intensity of our vector RPB. That is, this distance over here is R. Next, let's express x as p. Let's see from here. X as p is obviously r multiplying cosine of this angle, theta plus beta. So let's write it here. On the other hand, y s p is r multiplying sine of theta plus b. Next, let us recall the basic formula for the cosine and sine of two angles. We have cosine of theta plus beta is equal to, let's see, this is equal to cosine of theta multiplying cosine of beta. Then we will have minus sine of theta multiplying sine of beta. Good. This is the first formula. The second formula is cosine, or better to say, we need actually sine. Let me correct this. So we have sine over here, and we have theta plus beta, and this is equal to sine theta cosine beta. Then we have here plus cosine theta, and we have sine beta. If we substitute these two formulas in these two equations, we obtain the expression for x as p and y as p. You can see them over here. Next, let's analyze what is r cosine beta and what is r sine beta. Let's analyze this figure. From this figure, we can see that x b p, that is this distance over here, is equal to r cosine beta. This is very important. Similarly, we can see that YBP, that is this distance over here, is simply r sine beta. This is a very important observation that will enable us to significantly simplify these two equations. So let me now draw a straight line, and let's analyze what's written over here. Let me change the color. Over here we can see that this term multiplying cosine beta is actually xbp. Very interesting. Then we can see over here that this term r multiplying sine beta is actually ybp. Similarly, we can see that this term multiplying cosine beta is again xbp, and over here we can see that r multiplying sine beta becomes ybp. And this is a very important observation. Consequently, we can write x as p, that is this projection over here, is equal to cosine of the angle theta multiplying xbp, that is multiplying this projection over here. Then we have minus sine of theta multiplying ybp, that is multiplying this projection over here. And this is our first important equation. The second equation is obtained in the similar manner, that is y as p is equal to sine of the angle theta multiplying xbp. Then we have plus cosine of the angle theta multiplying ybp. These two equations can be written in the matrix form like this. On the left hand side, we will have the vector x SP and YSP. Then we will have a matrix, and here's our matrix. It's going to be cosine theta, then we'll have minus sine theta, then over here we will have sine theta, and then we will have cosine of theta. Then we will have that this matrix will multiply a vector, and this vector will be x BP and YBP, and that's it. Next, it's very important to observe the following. This vector over here is actually our original vector RPB, and let's write it down here, RPB, and we can see that the projections of the vector RPB are expressed in the coordinate system B. This matrix over here is denoted like this, R of the angle theta, and we have this famous notation B with respect to S. This is the rotation matrix. So let's write it down, rotation matrix. And over here on the left hand side, we actually have our vector RPB, however, this time expressed in the coordinate system S or in the frame S. I will write this vector like this, R, since it's a distance, P, since the endpoint is P, however, this time this vector is represented in the coordinate frame S. We can see that these two quantities are actually the same vector, nothing changed, only their projections are different since we consider two coordinate systems that are actually different. And consequently, we will have this equation over here. And let's write this equation compactly, so we can write RP with respect to S is equal to the rotation matrix that will transform B into S. This rotation matrix depends on theta, and we will have multiplying by RPB. What is the meaning of this equation? This equation will actually take the coordinates of the point P, that is, it will take this vector, then it will multiply this vector by this rotational matrix, and it will produce the coordinates of this point P in the coordinate frame S. Okay, let's proceed with the second step. In the second step, we will derive the expression for RPF that will depend on this rotation angle and on this translation vector. So let's do that. First of all, let's express the vector RPF by using basic vector algebra. We can write RPF is equal to, let's see, it's actually equal to RBF plus what? This is very important to clarify. What do we need to add here? Now, a naive approach would be to simply write this thing, RPB. However, this is a mistake. Stop here for a second and think why this is a mistake. The mistake over here is that the coordinates, or better to say the projection of this vector RPB, are expressed in the coordinate system B, that is in the body frame. If you remember, this vector over here has the coordinates XBP and YBP, and these coordinates are actually given over here. This thing is XBP, and this distance over here is YBP. That's why we are not able to add these two vectors, and this is the error. So let's go back a few steps in the past. I will simply erase this automatically, and let's see what needs to be written over here. Over here, I will write this. I will open these angle brackets, and then I will write my vector RPB. However, over here, I'm going to introduce a vertical line and say the following: expressed in F. So this term over here is not exactly RPB expressed in B, this is RPB expressed in S. Now, we have shown that this vector RPB expressed in F is actually equal to RP in the frame S, and this frame S is translated with respect to F. That is, the the coordinate axes of S and F are parallel to each other. And let's sketch S over here. Here's our S. Consequently, we can write this. RPF is actually equal to, let's see from the graph, it is RBF plus vector RP with respect to S. And this is very important. Now, if we go one step back and if we analyze the rotation matrix equation, we can see that this term over here can be expressed as a multiplication of the rotation matrix and RPB. That is this vector over here. Consequently, we can write RPF is actually equal to RBF plus, and let's write it nicely, we will have the rotation matrix that depends on theta. We will have the transformation from B to S over here, multiplying over here this term RPB. And this is what we shown previously. Now, this rotation matrix R, B to S is actually equal to the rotation matrix from B to F. Since we can see F and S as equivalent frames when it comes to rotation, translation is not taken into account. Consequently, we can write RPF is equal to RBF plus, over here we will have R, B to F with respect to angle theta, multiplying RP in B. And this is a very important equation. This equation can be compactly written like this. Let's write it in the matrix form. Over here on the left-hand side, I will have a vector. It's going to be actually a block vector. The first block entry is RPF, and over here, the second block entry will be a simple scalar 1. Okay, then I'm going to draw here a horizontal dashed line to denote these sub-blocks. Then, on the right-hand side, we will first have our matrix, and this is our homogeneous matrix, and we will have R, B to F of theta. Then we will have over here this translation vector as a new block RBF. Then over here in the second block row we will have 0 and 0. This is because this matrix RBF is a 2 by 2 matrix, and we need to make the dimensions of this matrix to be consistent. Then let's now draw this vertical dashed line to denote the blocks, and over here we will have 1. This is because RBF is actually a vector. And let's close this matrix. Then this will be multiplied by this thing. It's going to be multiplied by, let's see, over here I need to multiply r theta b with respect to f by the vector rpb. Consequently, I need to write rpb. And here it is. And then to make all the dimensions to be consistent, over here I need to write 1. And that's it. This matrix over here is our homogeneous matrix, denoted like this. T transforming B into F. We can see that this matrix depends on theta or theta, and it will depend on this translation vector over here, which I will simply denote like this, RBF. That is this translation over here. To summarize, this matrix over here is called the homogeneous transform matrix. And let's write the last equation compactly. The last equation can be written like this. We will have R, P, F. That is the distance from here to here expressed in F. Then we will have 1 over here. Then on the right hand side we will have our matrix T, B with respect to F. Usually we omit this dependency in order to ease the notation, and over here I will have the vector RPB, that is the vector RPB with the coordinates, or better to say with the projections expressed in B, and I will have 1 over here. And that's it. By deriving this equation, we arrived at a very important conclusion. We can take the coordinates of the point P in the coordinate system B, and these coordinates are encoded into the projection of RPB. Then we can simply form our homogeneous matrix or homogeneous transform matrix. We can multiply this vector encoding the coordinates of P in B, and we can obtain over here the coordinates of P in the fixed frame F. That is, only a single matrix multiplication will perform translation and rotation. Next, it's very instructive to learn how to completely expand this equation and this matrix. And for that purpose, we need to introduce the projections of our vector RB in F. This projection, that is the distance from here to here, is denoted like this. It is XFB. Then this projection over here, that is the vertical projection, that is the distance from here to here, and this is the projection of RBF onto the YF axis, is denoted as YFB. Previously, we have also projected our vector RPB onto the B and onto the S frames, and just stop this tutorial, go a few minutes before, that is in the past, and you will see these projections. And over here I will write everything. So let's see the result. Let's expand this vector over here. We will have the projections of the vector RP in the frame F are given over here. Let's sketch them here. This distance over here is actually XFP, and this distance over here, let's nicely write everything, that is the distance from here to the F point, is X, let's write it here, XFP, or actually it's Y, Let me nicely write it down. It is y, f, p. Okay, so we will have rp expressed in f with its projections becomes x fp. Okay, then we need the y projection, this projection, y fp. Then we will have 1 over here. And let's make a block here. And let's actually use dashed lines for our block. Then what we will have over here? We'll have a matrix. And let's write all the entries of this matrix. First of all, we need to go back and recall how does the matrix RBF look. It looks like this. We'll have a cosine of theta, then we will have minus sine of theta, then over here we will have sine of theta, then we will have cosine of theta. Then we will have 0 and 0 over here. Next, we need to enter the projections of the vector RBF. Here's the vector RBF, and its projections are XFB. So let's write XFB. And another projection onto the YF axis is YFB. And over here we'll have 1. And this is the form of our homogeneous transform matrix. Then we need to multiply this by this vector over here inside, and we will have its projections. We will have the projections of the vector RP on B. Over here I'm going to simply sketch them. So over here is one projection. This projection is denoted as XBP. And over here I will have another projection, distance from here to here, and this distance is YBP. Consequently, we will have XBP and we will have YBP over here, and then don't forget this one over here, and that's it. Simple as that. And you can see that the blocks are properly partitioned by analyzing the structure of this matrix. You can, for example, start from here and you can see the dimensions are okay. Namely, this is the rotation matrix 2 by 2, and this vector over here from here up to the top is actually 2 by 1. So we can multiply this by this vector, no problem. Then you will also see that other dimensions are also consistent and there are no issues. Namely, if you multiply this row by the vector, you can see that this is possible since we will have 3 columns and 3 rows over here, as well as over here and over here.